Welcome to tonight's lesson. So in this lesson, we are going to continue with looking at the equilibrium of a particle. But what we are looking at today is three dimension. When you have a particle that is being located in a 3D, or yeah, okay, let me put it that way, because last time when we met, we were discussing equilibrium of particles, and we're just looking at 2D, two dimension. So today we're going to have three dimension, meaning we're going to be having the X, Y, and Z axis. Then apart from that, we'll also be having the IJK notation when it comes to Cartesian annotation of the position of the particle. All right, so let's quickly begin. So if you have any questions or you want to know more about the lessons, you want to join the online lessons that I teach, you can use these contacts on the screen to contact me. Yeah, so let's quickly get into business. So one of the most important things that you need to understand when you're dealing with equilibrium is the equation that summation of all forces in, let me do this, okay. So you have to understand that for anything or any particle that is in equilibrium, for any particle that is in equilibrium, you have to understand that summation of all forces, okay, let me just do this. Okay, so summation of all forces should add up to what? Should add up to 0. What this means is that all the forces in the X plus all the forces in the Y plus all the forces in the Z axis, these are all supposed to add up to 0. Then when you get independent summations of these forces, you are also supposed to equate them to 0, because their forces are also going to be adding up to 0. Because anything that is in equilibrium means that it's not it's like in a stable state. Yeah, it's like in a position where it can neither move where it can neither increase, if we're talking about speed, to neither increase the speed or decrease. Or if we're talking about the position, to neither go to the left nor to the right. It will just be in one position, meaning it's not moving, meaning that the forces or the summation of all the forces that are acting on that particle is simply just going to be equal to 0. Nice. Okay, so this is what we are going to be looking at tonight. So let us quickly look at these equations. So this is what I was talking about. If you have this particle in space and you're trying to locate these particles, if you have the respective forces, you have F1, F2, and F3. All the forces that are acting on this particle in space are supposed to add up to what? Add up to 0. This is the reason as to why we use this expression here. Yeah, so we know to say anything that is in equilibrium, when you just hear about equilibrium, either in physics, statics, or anything that has to do with physics or science, anything that is in equilibrium is going to have all the forces that are, all the forces acting on that object are supposed to add up to what? 0. Okay, so this is what I was trying to talk about. All right, so let's quickly look at some of the questions that are talking about the same equilibrium thing. Okay, so the first question that we have here is a 90 pounds load is suspended from a hook, from the hook shown in the figure 3.10a. If the load is supported by 2 cables, so the load is being supported by 2 cables. When you check, the load that we have here is just this part here. So, and this load is being supported by what? By 2 cables, and what? And the spring having the stiffness 500 pounds per feet. So we have 3 cables supporting this load, and we also have a spring. So we have 3 cables supporting this load here, which is 90 pounds, and also 1 spring, which has the spring constant K, which is equal to 500 pounds per feet. Okay, so the question goes on to say, determine the force in the cables and the stretch of the spring for equilibrium. So they are telling us to say this force here, or this load here, is in equilibrium, meaning it's not moving in any direction, it's stationary there. What that means is that we have all the forces that are acting on this load here adding up to what? Up to 0. So this is what we are going to use as our basic, this is what we're going to use as, to get our solution. We know that all the forces are supposed to add up to what? 0. So let's do that. So we know that all the forces are supposed to add up to 0 since the load is in equilibrium. Then we know to say the force of a spring is given by what? By K times what? Times the stretch. So the stretch here is just a change in the distance of, not really the distance, but it's just okay, let me just call it distance for lack of better terms. Okay, it's just the distance that this spring will stretch when the load is in equilibrium, yeah, from its initial state. All right, so let us see quickly what we can do, or how we solve such a question. So how do we solve such a question? So these are very simple questions. Okay, so we start. So we get first the summation of forces in the x. Summation of forces in the x, we know that they're supposed to add up to what? 0. So let's take the forces in the x. So the forces in the x, when we start with D, the force in the x for D, so I'm going to say FD. The forces in the x for D, I'm going to call it FD. So for D, for the rope, this rope D, in the x, we have, so the x-axis, our x-axis is simply just this. So in the D, we have what? We have this distance this side. Let me change the color so that you see what I'm writing. So the x-axis is simply just this one here. And the force, the forces in the x for the rope D is simply just this component this side. So this component, if you check it, it's parallel to this one. So I'm going to use this one because this is where the angle has been given. So now, since it's parallel to this and this is opposite to the angle, when you're dealing with SOHCAHTOA and you are dealing with the force here, which is the hypotenuse, and the opposite there, which is the opposite to this angle here. So whenever you're dealing with the hypotenuse and the opposite, you use sine. So we say FD sine what? Sine FD sine, let me use white. So we say FD sine. So we have FD sine sine 30. And then we move on to, do we have the component, the x component of C? Do we have the x component of C? Yes, we have. So when you look at, do we have the x component of C? Yes. When you look at C, C has moved how many units? It has moved 4/5 units in the, 4/5 units in the, it has moved 4/5 units. So we're going to have, and it has moved in the negative, because the x-axis, when you look at it, the positive x-axis faces this side, the negative x-axis is that side. So C has moved this distance there, and the triangle given there is this one. And the part representing this, direction here is simply just that 4. So we are going to have 4, so it's in the negative x-axis, and then we have 4 over the hypotenuse there, which is 5. Then we're multiplying this with what? With the force FC. Then we say this is equal to 0, because these are the only forces that we have in the x. The spring is only in the y if you check. The spring is only in the Y. That's why I've not considered the rope B or the spring itself. So these are the forces that are in the X. So let's quickly find the forces that are in the Y. So the forces that are in the Y, they are also supposed to add up to what? Up to 0. So the forces that we have in the Y component, one of them that we have is what? Is the same spring. So the force that is in this spring, I'm going to call it what? FB, because of this B there. And then do we have another force that is in the Y? Do we have any force that is in the Y from what's this, from D? Yes, we do. So in the Y we have it's actually going towards the negative. So we have negative FD cos 30. Why am I saying cos 30? When you look at this force there, when you look at the force, the component of this force along this rope, in the y-axis is this one here. It's facing the negative y-axis and it's adjacent to the angle 30 there. That's why I've used cos there. And then from there, the other thing that we need to find is the component, the y component of the force in the y-axis in the rope C. And when you look at the rope C, it's only in the x and in the z axis. Hence, we just leave it like that because we don't have its component in the y. So we say this is going to be equal to 0. Then we also find the summation of forces in the what? In the z axis. So the summation of forces in the z-axis are also supposed to add up to 0 because the particle is in equilibrium. So what we now have to do here is, in the y, what forces do we have in the y? So what forces do we have in the y? So in the y, the first one that we have is this same weight that we have, the load. The load itself there, which is 90 pounds. So 90 pounds is facing down. So we have 90 there. Of course, it's going to be negative 90 because it's facing down. So we have negative 90. So we have negative 90. And then the other force that we have in the y is the force along the rope C. So we have FC there in the y. So FC is facing towards the positive, not really in the y, in the z-axis. FC is facing towards the positive z-axis. So we have a positive there. And then we have FC, but because, and then the side that is representing the z-axis of this rope is simply just 3 there. So we have open brackets 3 over the hypotenuse, which is 5. Then we say this is equal to what? 0. So now we can find the values of the forces in all the ropes, FC, FB, and FD. So now how do we do that? This is simple. So we just take this negative 90 to the other side of the equal sign because this is where we only have one unknown. That's why I've started with the third equation here, because in these two equations we have two unknowns. So we start with the one that has the least number of unknown forces. Okay, so when this force moves to the other side of the equal sign, you have FC 3 over 5 being equal to 90. So when you cross multiply there, you're going to have 30 times 5, which will give us 150. So our first force, which is FC, it will give us what? When you do the cross multiplication there, 5 times 90, that is going to give you 450. 450 divided by 3, that will give us a 150. So we have 150 pounds. That is our first force. And then we can replace this in we can replace it there to get the value of FD. So FD will therefore be equal to, so when you put 150 there, we're going to have something like this. We're going to have, when you put 150 there, we'll have 5 into 150. So let me put it there. Because of lack of space, I'll just be deleting what I have already there. So if I put that there, 5 into 150, that is going to give me 30. 30 times 40. So 30 times 40, this is going to give me what? So 30 times 40, this is going to give me, rather 30 times 4, this is giving me 120. Yeah, so this will give me 120. So the 120 that you find here will cross the equal sign, and then you divide everything by sine 30. Sine 30. So when you divide everything by sine 30, FD will remain this side, and sine 30, that is simply 0.5. When you divide that by 0.5, you have 240 pounds as the force here. Then we move on to this one. So now that we have FD, we can just replace it there. Then we have FB being equal to what? So you have, when you put 300 there, say cos 30 times 300, that is going to give us what? The value for, oh, not 300, when you put a 240 there. So 240, that is the value of FD. So 240 times cos 30, that will simply just give you what? It will give us, so trying to find FB. So that is just going to give us, I don't have a calculator, so I'll just write 240 cos 30 as the solution there. So this is our solution for FB. So now the question is also asking us, okay, we have managed to find all the forces in the ropes. Now the question goes on to ask us to find what is this? Where is the question? Okay, it's saying determine the force in the cables and the stretch of the spring for equilibrium. So we've also been asked to find the stretch. Remember this formula which I wrote there. This is the formula for what? For the force that is in the spring. So in the spring we have K and S. So K has been given, and then we're trying to find S. Then the value of F is simply just the force that is in B. So the force that is in B is simply what you have found there. So we will simply just have to replace the figures there. So while there is force there, I'm going to put my 240 cos what? Cos 30, and then this will be equal to, the value of K has been given there. The value of K is what? Is 500 pounds. So the value of K is 500 pounds. Then I'm multiplying this with S. So I'm trying to make S the subject of the formula, and the value of S was therefore be equal to, so this is the stretch I'm finding. So the stretch is therefore going to be equal to 240 cos 30, everything divided by 500. So the stretch will therefore be equal to this and that to cancel. So you have 25, the numbers that can go there. So we have 2 into 24 and 2 into 25 there. So 2 into 24, that will be what? 12 over 2 into 250, that will be 25 times cos 30. So this is our stretch. So you can use your calculator to find the value for the stretch. What I've written here, you can punch on the calculator and find the actual value. So this is our stretch, and it's in feet. All right, thank you very much. Let's quickly move on to the next question. So this is how you solve such questions. Very simple and straightforward. Okay. So these are the forces that we have found. And then the stretch, like I said, you just equate the force that is in B to K times the stretch in AB. Okay, let's quickly move on to this question. So this question is also a very simple question, and it's asking us to determine the force that is in each cable, the force in each cable used to support the 40 pounds crate. So how do you determine the force that is in the cable? How do you determine the force that is in each cable here? Okay, so how do you determine? Okay, this is also a very simple question. So here, what we've been given is the crate there and its weight. Its weight, or rather its force there. Let me say its weight or the load has been given. So We are also going to use the same equation, which is summation of forces. So summation of forces should be equal to 0 because the crate is in equilibrium. So the crate is in equilibrium, and we're going to use this same equation to find the solution. So having been given the positions of these cables, what we need to find is the unit vectors. So we need to find the unit vector along the cable AB, the unit vector along the cable AD and the cable AC. So when you find the unit vectors, then we multiply by their forces. Then after multiplying by their forces, we solve the resulting equations simultaneously to get the values of all the forces. So we start with the forces that are in the X. So the forces in the X, before we do that, let us first find the unit vectors along each of these cables. So the unit vectors along these cables are simple. So let me find the positions of these points that we have, point C, B, and D. So the point C is, okay, let me just say the point C, I'll call it FC, or rather the vector along FC. Or let me just find the unit vectors in advance. So the unit vector along C is therefore going to be equal to, first we find the coordinate of C in space. The coordinate of C in space, in the X, it's moving how many units? So in the X, it's moving 3 units. Then in the Y, it's moving how many units? 8 units, rather in the Z, 8 units, going towards the positive, and then the X is negative because it's going this side. Then in the X, rather in the Y, it's moving 4 units. 4 feet. So let's quickly now put that into that. So we have in the X, we said it's 3, but because it's going towards the negative X, we put negative 3i. And then in the Y, we said it's 4 and it's going towards the positive. We put the positive, it's moving 4. We put the positive 4j. And then in the Z axis, it's also moving. Yeah, so in the Z axis, it's moving 8 units going up. So 8 units from the center, or 8 units from the, okay, 8 units going, it's moving 8 units going up. So we have, and it's moving towards the positive Z axis. So we say plus 8k. And then we're dividing everything because it's a unit vector. We divide by the magnitude of this same vector. So we say over the square root of negative 3 squared plus 4 squared plus 8 squared. So now this is now simple to find. So we find this is a unit vector in the direction of in the direction of the rope, in the direction of the rope C. So now to find the vector itself in C, or the force that is in C, you multiply this same vector by what? By the force. So we multiply the vector by the force, and this force is not known. So we are just going to call it FC. So this part is 9 plus 16, 25 plus 64. So 16 plus 9, that is 25. So 25 plus 64. So you have 64 plus 25. So 64 plus 25, that's 89. So the unit vector, or rather the force in the rope C is simply just going to be what? Is simply just going to be negative 3 over the root of 89 plus 4 So we have I, then we have j there over the root of 89, then plus k. This would be 8k over the root of 89. Yeah, so this is one of our vectors. So don't forget to put FC there. FC, FC. Okay. So after finding this is our first equation. Or before we start naming the equations, let me just say this is the force in this cable. And then we also find the force that is in the cable B. So we also do the same. We first find its unit vector. So its unit vector, we have negative 3I, and then its y component is negative. So we have negative 4j because it's going towards the negative that side. And then we have positive 8k. Then we're dividing everything by the square root of the same expression there. So negative 3 squared plus negative 4 squared plus 8 squared. And then to find the vector along that expression, we multiply by the magnitude of the force C. Yeah, so we have that. So from there, we have something like this, and this is going to be equal to, so we have negative 3 over the root of 89. So we have negative 3 over the root of 89. I, then we have this multiplying by what? By FC. Then we have minus 4 over the root of 89, J multiplying by FC as well. Then, oh, sorry, not FC. We're dealing with B here. So we are multiplying by FB. So this is our FB. And then we also have plus 8 over the root of 89 FB. So this is in the K. Then after doing that, we also find the position vector of, along the force or the rope D, or along the cable D. So we say FG is equal to, so FD is equal to what? FD is going to be equal to, it's only in the x-axis. So FD is only in the x-axis, and it's moving, and it has the magnitude of what? So this one is having the magnitude of what? I can't see the figure representing FD. Where is it? It's in the x-axis, of course, meaning we know that it has I. I'm trying to see the magnitude of FD. Okay, do we have the magnitude of FD shown in the figure? Okay, so yeah, all right. So this part here, I've just remembered this one is along the x-axis. So if it's along the x-axis, it means that the unit vector of any, or the magnitude of the unit vector of any force along its axis is 1. So we know that the unit vector has actually the magnitude of 1. So we just multiply 1 times I, that is I, and we have the what's this? The magnitude of that force, which is FD. So, and that we have there. So, and then we also need to find the position of the weight in space. So the weight is simply just equal to, it's in the, so the weight is in the z-axis. So in the z-axis, and its magnitude is 40. So we just say 40 times k, because it's only in the z-axis, and it's in the negative z-axis. So we add the negative there. Okay, so from there, the next thing that we just need to do here is to find the summation of all forces in the x, in the y, and in the z. You put them together, and then you equate everything to 0, and later find the values of FC I mean FC, FB, and FD. So you get all the X components, you get this, you add it plus that, then plus that, then you equate it to 0. So what I'm trying to say is you have negative 3i, let me not be putting the i's. So we have negative 3 over the root of 89. Then you also have negative 3, another negative 3 over the root of 89. And then so the first one has, sorry for that. The first one is having FC, so this one is FC. Then we have another negative 3 over the root of 89 FB, so this one here. Then the other one which has the X component is FD, so we say plus FD is equal to what? 0. So this is our first equation. The second equation will also be formed from getting the Y components. So we have 4 over what? The root of 89 FC. Then you also have negative 4 over the root of 89 F what? FB. Then we have anything in the Y this side, we don't have. So we just say this is equal to 0. So this and that can cancel. So we know to say FC is equal to FB. So this tells us to say FC is equal to FB. And then the other thing that we need to do is to get the Z components, the Z components, yeah, which are the K components here. So the first one we have is 8 over the root of 89 FC. And then the other one is 8 over, so we have 8 over the root of 89 FB. And then the last one that we have is negative 40. So we say this is equal to 0. So this can go that side so that we just remain with 8 over the root of 89 FC, then plus 8 over the root of 89 FB is equal to 40. So this is what we have. So we have this equation, we have this equation, and that equation. So now it's just a matter of solving these three equations simultaneously. So if you have a calculator, that is a very simple thing to do. So you can solve this, that, and that equation simultaneously. And then when you solve them simultaneously, the solution that you're going to get is, the solutions for FC, FB, and FD that you're going to get are the ones that they actually want. So those are the forces that they want you to determine that are in the cables. All right, so this is what I prepared for tonight. So thank you very much for watching tonight's lesson. See you in the next lesson that we are going to have. And make sure that if you have any questions or you have any challenges that you want me to help you out with, or you want to join my tuitions group, feel free to simply just contact me using these same lines on the screen, and we are going to help each other. Okay. See you in the next tutorial video.